Good day, viewers. It's good to have you in class today. My name once again is Dr. Chris Esekaibe. Today we shall be looking at a topic titled linear correlation. In our last class, the last video I uploaded, we looked at linear regression, linear curve fitting, and fitting a straight line. We were able to look at the relationship between those topics. Today we shall be looking at linear correlation. Once again, I welcome you to today's class. My name is Dr. Chris Esekaibe. Please subscribe to my YouTube channel, Dr. Chris Esekaibe. My YouTube channel consists of so many videos that have topics in statistics and mathematics, most especially numerical analysis. I hold a doctorate degree in mathematics, a master's in mathematics, and a bachelor in statistics. I am a chief lecturer in one of the most prestigious polytechnics in Nigeria. I work in Nigeria, I live in Nigeria. My area of specialization is numerical analysis. I also specialize in data analysis and modeling, scientific computing, and statistical analysis. You can consult me with any of your research work. Peradventure, you are a research institute in any part of the world, any speaking English country, in any English speaking country. I speak English and I do my work writing in English language. If you are a research institute, you can consult me. I am a consultant in numerical analysis, data analysis and modeling, scientific computing, and anything that has to do with statistical research. If peradventure you are an AI firm, you deal on artificial intelligence, we can work together as a team to develop advanced mathematical or statistical algorithms for artificial intelligence or models for artificial intelligence. I'll be looking forward to hearing from you. I'm a member of the Nigerian Mathematical Society, and I'm also a member of the Nigerian Statistical Association. I've authored quite a number of books: a first course in numerical analysis, advanced or applied statistics for business sciences and engineering, a first course in linear programming, also a first course in mathematical methods, and also I wrote a book on functions and geometry. So contact me with your work. I will be looking forward to hearing from you so that we can work together as a team, especially in the area of building mathematical and statistical models or algorithms for artificial intelligence. If you're a research institute, why not consult me? My name is Dr. Chris Esekaibe, the doctorate degree holder in mathematics. Numerical analysis is my area of specialization. Then I hold a master's degree in mathematics and a BSc, a bachelor degree in statistics. Here are my contacts. You can contact me on any of these two numbers. They are also my WhatsApp numbers. +234. Please put this code, it's for Nigeria. +234 80 330 21903. It's the WhatsApp number, or you can contact me on +234 7066 297535. It is also my WhatsApp number. You can reach me on this email, chrisdavids2015@gmail.com. I will be looking forward to hearing from you. It's good having you in my class today. God bless you. Please subscribe to my YouTube channel. Click on the notification button. Share my videos in your social media platforms. And as you do, God will bless you. So let's go quickly to look at what we have today. Today, we are looking at linear correlation. Linear correlation. In our last class, we talked about linear regression. Regression studies the relationship. Linear regression studies the relationship between two variables. We were able to look at the two variables y and x. We looked at a situation where y is depending on x We also looked at another situation where X is depending on Y, and we're able to get a model, and we looked at the intercept and the slope. We explained what they meant. So today we shall be looking at linear correlation. There are two different formulae for linear correlation. Please wait patiently and watch this video to the end. At the end of this video, I can assure you, you will be able to know the difference between Pearson Product Moment Correlation Coefficient, RO, and Spearman Rank Correlation Coefficient, that is denoted by P of RHO. Now, you will know when to use the two different formulae, when to use it, and when not to use it. So please wait patiently to the end of this video. The Pearson Product Moment Correlation Coefficient was developed by a British biometrician stroke statistician called Carl Pearson. So this formula, and this is the formula for linear correlation, and the linear correlation is denoted by small letter r. So r of x, y, x and y are the two variables, is given by this formula here. N summation x, y minus summation x, summation y all over square root of n summation x square minus summation x all square bracket open, n summation y square minus summation y all square bracket close. So this formula was developed by a British biometrician stroke statistician called Carl Pearson, and it was named after him, Pearson Product Moment Correlation Coefficient. Then this other one is given by P into RHO 1 minus 6 summation D square all over N into N square minus 1. This other formula, these two formulae are for correlation, are for linear correlation coefficient. This second one is also developed by Charles Edward Spearman. Charles Edward Spearman. So the Spearman Rank Correlation Coefficient is denoted by this, and it was developed by this British psychologist. So Charles Edward Spearman was a British psychologist that developed this formula here. As we proceed in this class, you will see the reason why Charles Edward Spearman came about this particular formula, the reasons why he developed it. So please take note of my contacts as I clean this part of the board so that we can go deeply into the business of the day. I'll be looking forward to hearing from you, and it will be good to work with you as a researcher in my area, in my country, and as an academist, and also one that have reached the peak in the polytechnic system in Nigeria. What you see me do in my YouTube channel is a display of my wealth of experience I've been able to acquire over the years, the past 20 years of my lecturing and in Nigerian tertiary institution. I've been privileged to lecture in the university, and in an open university, also in an A-level college in Abuja, Nigeria, and I've been in the polytechnic system since 2007 till date, one of the renowned federal polytechnic in Nigeria. So please, now let us see what we mean by correlation, or let me write it again, linear correlation. I told you in our last video that linear regression studies the relationship between two variables. But when we talk about correlation tells us the strength or the degree or the direction of such a relationship. So linear correlation tells us the degree or the strength. It tells us the degree, the strength, stroke direction of the relationship between X and Y. So the two variables are X and y. So linear correlation tells us the degree or the strength or the direction of the relationship between x and y. I'll be telling us why Charles Edward Spearman came about this rank correlation coefficient formula. Now, the value of correlation is given between -1 less than or equal to the value of the correlation less than or equal to +1. So when you calculate using any of these two formulae, the correlation coefficient is a coefficient. Here it is denoted by arrow subscript xy. Here it is denoted by P into arrow HO. That when you calculate the value for arrow, it must fall between -1 and +1. It is not permitted to go below -1 and it's not permitted to go above +1. If you, for instance, you calculate arrow to be equal to +1, it means a perfect positive relationship. Then, if you calculate your arrow to be equal to -1, it means negative, a perfect negative relationship. Now, you should know that the value of arrow is not permitted to go below -1, and the value of arrow is not permitted to go above +1. And when you calculate the value of arrow to be equal to 0, it means there is no evidence of any relationship. When arrow is equal to 0, it means there is no evidence of relationship. So it is good we begin to see how this works. Now, in a situation where you are given tabular values of x and y, and you are now told to calculate the correlation coefficient R, the question is, when do I use the Pearson Product Moment correlation coefficient? And the other question is, when do I use the Spearman Rank Correlation Coefficient? When do I use either of these two? Do I just pick any one of the two formulae and start using? As we progress, you will understand. Now, permit me to clean this part of the board as I explain linear correlation further. Now, we can use what we call scattered diagram or plotted graphs. Scattered diagram or plotted graphs to explain. If I have a graph as this, of course, this is my x-axis, this is my y-axis, then there is I'm able to get a straight line like this. The plots are facing this direction of the straight line, all the plots of the observations. Of course, when you have x and y, you plot it and it's passing it, and you have a straight line facing this direction, then these indicate positive relationship. If I plot another graph, or if the graph is taking this direction, this is my x-axis, this is my y-axis, I plot the variables, and it's now taking this direction, giving me a straight line like this. The closer the value to the straight line determines what the value of arrow is. And I have this is bending like this. This means negative. It means negative relationship. That is what it means. If it's going like that, then if I plot and I have a graph as this is my x-axis, this is my y-axis, and I have it like this, it's just scattered around like that. This one means no evidence of a relationship. That is what it means. It means no evidence of any relationship. So if we have this, now you can use the scattered plot or the scattered diagram to check, to have an idea of what the relationship is. If it is going like this, from downward, upward, this way, it is, the relationship is said to be positive. We may not know the strength of the positivity, whether it's 1 or 0.8 or 0.9 and so on and so forth. I'm going to tell us or show us how we interpret the value of arrow after calculating it. Then when it goes like this, it indicates negative relationship, and if it goes like that, that means it's parallel. In a way, it means there is no relationship. It means there is no evidence of a relationship. Now, permit me to explain further. When do I use the Pearson Product Moment Correlation Coefficient by Carl Pearson using this formula? When do I use the Spearman Rank Correlation Coefficient by Charles Edward Spearman? Now let us go into that. Watch carefully, listen attentively, so that you will understand when to use any of these two formulae. Now, I will start with the Pearson Product Moment Correlation Coefficient. The first thing you need to check when you are given a set of data, the data set must be continuous. That's the number one proof that it is the Pearson Product Moment Correlation Coefficient that you are going to use. This particular formula studies the degree or the strength or the direction of the relationship. It will tell you the direction of the relationship, the strength of the relationship between, or the strength of the linear relationship between X and Y. This one is for linear. It's not multiple correlation, it's for linear. So the data, now what do I mean by continuous data? Continuous data are data that can be measured in numbers. They are measured in numbers, and they are quantitative in nature. So they are measured in numbers. E.g., you have your weight, you have your height, and so on and so on. You have your scores, and so on and so forth. So they are measured in numbers. And continuous data are data that are given within a range or interval. So continuous data are given within a range or interval, so they can be measured, they are quantitative, and so on and so forth. That's what we mean by continuous data. That is when you see that the data X and Y are measured. They can be scores from tests or from an examination. They can be age, they can be height, they can be weight, they can be anything that is measured, data that is measured. That is when you will make use of the Pearson Product Moment Correlation Coefficient. That is when we make use of that. So to test the linear relationship, the direction, the strength, and the strength of the linear relationship. Now, when do we now use the Spearman Rank Correlation Coefficient by Charles Edward Spearman? By Charles Edward Spearman. You will agree with me that there are certain data that cannot be measured numerically. So we use the Spearman Rank Correlation Coefficient for qualitative data. Data that cannot be measured in numeric form. I give an example Example, beauty. Example, intelligence. Intelligence, character, behavior, and so on and so forth. These data are qualitative data. They cannot be measured in numeric form. So when this formula came up by the British biometrician and statistician, it was used for continuous data. Then Charles Edward Spearman now thought it wisely. How do we now analyze data? How do we now analyze data that cannot be measured in numeric form? Data that are qualitative. Now we want to study beauty, we want to study intelligence, character, behavior, and so on and so forth, anxiety, and the rest of them. How do we now measure them? How do we now study the relationship between, if we have two of such variable, how do we now study them? So it now came about ranking. So this one, they are used, the kind of data we analyze using the Spearman rank are ordinal data. Ordinal data. Or some author can call it ranked data. Data that are ordered, that are ranked. So we use them for data that are ranked. That's why you see the name there, Spearman rank. So the data must be ranked. So the ordinal data are ranked. They are put in order. So the data are qualitative data. And there is one, there are assumptions. Assumptions are that one, there is no tie in ranking. When you are ranking the data, for instance, if you are ranking beauty, for instance, you have 5 girls, you want to rank them based on their beauty. Now you start by giving the most beautiful person the first position, then the next, the second position, the next, the third position, the next, the fourth position, and finally the last person, the 5th position. Now, when you are using this for qualitative data that are measured qualitatively, like attributes like beauty, intelligence, behavior, and so on and so forth. These are attributes that are measured. When you are measuring this kind of attributes, the data you get from them are qualitative data, and the data must be in ordinal form or in ranked form before you use the Spearman Rank Correlation Coefficient. Now, for instance, I asked this question: have you ever come across any beauty pageant or any beauty competition where 2 people come as first position or 2 persons come as second position? No. So when you are using this Spearman Rank Correlation Coefficient, please take note of that. For qualitative data, there are no tie in ranking. No 2 persons, like I said, you want to rank the beauty of 5 ladies from first position to the 5th position. No 2 persons will take the first position. No 2 persons will take second position. So tie is not permitted in ranking of qualitative data. One beautiful thing about this Spearman Rank Correlation Coefficient, please take note, it can also be used for continuous data, for quantitative data. Quantitative data are data that can be measured in numbers. Example, age, height, weight, scores, and the rest of them. Then, why qualitative data are data that cannot be measured in numbers? They can be categorized. They can be ordered in form of various attributes or criteria. Now, when the judges that are to judge those 5 ladies based on their beauty, they will rank them from first position to the 5th position. And then there is no one, you can't say these 2 ladies are beautiful, are equally beautiful, so I give them, the 2 of them come first. No, for qualitative data, there are no ties in ranking. No ties in ranking. So you must take note of that. But when you are now dealing with quantitative data using this Spearman Rank Correlation, then you can break tie by taking the average of the ranks. You can break tie by taking the average of the ranks. So please take note of that. No two individuals are equally beautiful. No two individuals are equally brilliant. So that's why when you are, please take note of this, very important. That's where some statisticians miss it. That's where some statisticians miss it. When you are dealing with qualitative data for Spearman rank, there are no ties. If you are ranking, you rank from the first to the last. But now when you are now dealing with continuous data, quantitative data, there may be tie. I give an example. If you are dealing with age, for instance, it's possible to come across two people that are equal in age. They were born the same day. It's also it's also easy to see two people that have the same weight. It's possible to see two people that score the same in a particular exam. So in quantitative data or continuous data, it's possible to come about equal values, but not for qualitative data. So permit me to now pick an example. I will first of all pick an example to solve an example that has continuous data, so that we can use the Pearson Product Moment correlation formula first. Permit me to, I hope you have taken note of all this. So for the Spearman, we can use it to solve both qualitative and quantitative data, but when you are using it for qualitative data, there are no tie in ranking. You rank from the first one, from the first to the last. No two persons should have the same rank for qualitative data. But if you are using it for quantitative data, it is permitted. Quantitative data, two people can have the same weight, two people can have the same age, two people can have the same height, two people can score the same in an exam, and so on and so forth. Those are for the continuous data, the quantitative data. So permit me to pick up an example and solve and see how this can be achieved. Remember the example we used when dealing with linear regression analysis. I will bring about that data again. Then we are now going to use it to analyze. We have our X, we have our Y. Permit me to put it here. We have 10. I hope you remember this from the data 10, 10, 11, 12, 12. Then for Y, we have 5, 6, 4, 3, 3. So that is what we have. Now the formula will tell you what you need. We need summation x, y. We need summation x, which we will get from here. Summation y we will get from here. We need summation x squared. We need summation y squared. So we need summation x squared, summation y squared, and summation xy. So the first column we are having there, we are going to have our column for x squared, the column for x squared. So you are going to take each x. This will be 100. 10 squared is 100. 10 squared is 100. 11 squared is 121. 12 squared is 144. Then 12 squared is 144. Then the next one, we are going to take our y square. This is our y. 5 squared is 25. 6 squared is 36. 4 squared is 16. 3 squared is 9. 3 squared is 9. Then the last one that we need, we also need our xy. So you have your xy. Then you have it like this. So from there, your xy, 10 times 5 is 50. 10 times 6 is 60. 11 by 4 is 44. 12 by 3 is 36. 12 by 3 is 36. So now, let us sum to get their totals. The sum for for x is 55. The sum for y is 21. The sum for x squared is 609. Then the sum for y squared is 95. While the sum for xy is 226. 226. So you have that. So now we have been able to create this table, and everything we need in this formula has been done in that particular table. Now we want to study the relationship. Remember, we got the linear regression for y on x to be yc is equal to 17.95 minus 1.25x. If you watch the last video on linear regression, this was the model fitted for this value of x and y. This was the model, and our intercept was 17 or is 17.95, while the slope is minus 1.25. We told you that the slope is what determines the direction of the relationship. So the relationship between x and y was negative because the slope is negative from our linear regression that we did. So we have been able, from the linear regression, the slope will tell you the degree, will give you an idea of whether the relationship is positive or not. If at the being we got plus 1.25, it will be, that means the slope is positive, then there will be a positive relationship. So now, but the slope is negative. That's why you see that as x is increasing, y is decreasing, because the slope is negative. We were able to explain that in our last video on linear regression analysis, so linear coefficients. Now let us go ahead and calculate our linear correlation. So our arrow, permit me to use this side, arrow of x subscript xy will now be equal to, remember our n is 1, 2, 3, 4, 5. So our n is 5 into summation xy. Summation xy is 226 bracket 226, then bracket close, then your minus sign is here. Summation x is 55, then your summation y is 21, then all over bracket square root of, then you open a bracket. Our n is 5. Our n is 5. Our n is 5, then bracket. Our summation x squared is 609. 609. Then you minus. Then summation x is 55 minus 55 squared. Then you close the bracket. Then you open again. Our n is 5. Then our summation y squared is 95. 5 into 95 minus, then our summation y all squared. No, this is not summation y squared. Summation y squared is here from summation y all squared. Our summation y is 21 minus 21 minus 21 squared. Then you close the bracket. Minus 21 squared. Then you close the bracket. So we can now proceed to doing this arithmetic. So we come here, our arrow subscript SY, that is the Pearson Product Moment Correlation Coefficient, is now equal to 5 multiplied by 226 will give us 1130 minus 55 times 21 will give us 1155. 1155. Then all over square root of, if you carry out this multiplication, you are going to have, if you carry out this, you are going to have the square root of, you multiply this, subtract it from the square of this, multiply this, subtract it from the square of this. You are going to have square root of everything here will give you 20. This will give you 20. Then you put a bracket. Then you carry out the other one, that will give you 34. If you carry out this minus this, so when you now go 1130 minus 1155 will give you minus 25 all over square root of 20 by 34 will give you 680. Square root of 680. So when you now have this, you will now come and have your Rx subscript xy, that's is now equal to minus 0.98. Minus 0.98. What does this indicate? You can see that the relationship between x and y now is negative. It means that means it's highly negative. Are you getting me now? So this means highly, or you can say very high negative correlation between x and y. So it's the relationship is highly negative. So you can see that highly negative, and the slope here has told us that the relationship between x and y is negative, and the value of the correlation coefficient, the Pearson product, these data are continuous data. That's why we use the Pearson product correlation formula to calculate the linear relationship. So the linear relationship between x and y is highly negative. We told you if it is plus 1, it is perfectly positive. If it is minus 1, it is perfectly negative. Though this one is very close to minus 1, so we are not going to use the word perfect. It is when it is minus 1 that we call it perfectly negative correlation. So, but for this one, it's a very high negative correlation between x and y. Very high negative correlation between x and y. So now, I hope you have taken this. Permit me to go to do another example on Spearman rank. When do I use the Spearman rank correlation coefficient? Permit me to clean all this. I believe you have gotten something from this, from the Pearson Product Moment correlation coefficient R by Carl Pearson, who was a British biometrician and statistician. You use this when you have continuous data. The data are continuous, they are measurable, they are given in numerics, and you have it, and the data are quantitative. Why this data can be, this Spearman rank correlation coefficient can be used when the data are either qualitative or quantitative. I will show you how to go about it. So permit me to clean this. So I hope you have taken note of this particular example. So permit me to clean this particular one as we proceed with another example for the Spearman rank correlation coefficient, Spearman rule. Now, let us take this example. We can call that first one was example 1. Let's call this example 2. The 2 judges score 5 ladies in a beauty competition. The ranks are seen below. The ranks are seen below. So 2 judges. Now let these two judges be X and Y. So let the judges be X and Y. So now we are going to have the following data. These are the girls, and the girls are denoted to be A, B, C, D, and E. So these are the girls. Now we are going to get the ranks, because when you are ranking beauty is qualitative. There are data that are qualitative. So now let's look at the rank from the example, the rank of X, the rank from the first judge, Judge X. The ranks are given below: 5, 2, 3, 4, 1. Then the rank for Y, Judge Y, is given as arrow subscript Y. The rank for Judge Y, the ranks for Judge Y are 4, 3, 2, 5, and 1. That's what the rank for Judge Y is. Now look at it. Because the data are qualitative, the two judges have done a very good work. There are no ties in any of the ranking. Here, the girl E has the first position, followed by girl B, followed by girl C, followed by girl D, followed by girl A. Also, that's the ranking from the first judge, Judge X. Then the ranking from the second judge, girl E took first position, girl C took second position, girl B took third position, girl A took fourth position, and girl D took fifth position. You can see there is no tie here, because when you are ranking qualitative data that have attributes like beauty, intelligence, and the rest of them, there are no ties. Please take note of that. But when you are ranking continuous data, there may be tie, because continuous data are data that can be measured. They are quantitative. So when e.g. example, weight and height, two people can have the same height, it's possible. Two persons can have the same weight, it's possible. So you can experience tie when dealing with quantitative data, not qualitative data. So there is none of these two judges that will now come and say girl A and girl B are equally beautiful. It's wrong. There are certain criteria that must be used to judge them, that will make them to be different from one another, that will make each girl to be different from other girls, that will make them score either higher or lower. So these are the ranks, and there are no tie. So please take note, when you are dealing with qualitative data in ranking, when you want to use the Spearman rank, you don't have tie. Now we can now come and get our D. Our D is simply the rank of X minus the rank of Y. That is what D means, the difference. So 5 minus 4 is 1, 2 minus 3 is minus 1, 3 minus 2 is 1, 4 minus 5 is minus 1, then you come 1 minus 1, of course, is 0. Now, why are we having D? Look at the formula for the Spearman Rank Correlation Coefficient is 6 summation D square, as developed by Charles Edward Spearman, the British psychologist. N, of course, is the number of observation. So if it's not just D we need here, we need D square, the sum of D square. So we are going to create another column for D square. So you have it like this. So 1 square is 1, minus 1 square minus 1 times minus 1 is 1, 1 square is 1, minus 1 square is 1, 0 square is 0, 1 plus 1, 2, plus 1, 3, plus 1, 4. So the sum of D square is 4. So we can now come and get our Spearman Rank Correlation Coefficient, which is denoted as E into RHO it will now be equal to, now this one is separate. 1 minus 6 into summation, this square is 4, into, remember the girls are 5, A to E, so our N will be 5. So this will be 5 into 5 square minus 1. So this will now be equal to 1 minus 24 all over 5 square is 25. 25 minus 1 is 24. 24 times 5 will be 120. So this will be equal to 1 minus 24 divided by 120 will give us 0.2. 0.2. So our Spearman Rank Correlation Coefficient will be 1 minus 0.2 will be 0.8. So this one, our correlation coefficient is 0.8. Now, how do we interpret? So we can now say that our R is, it indicates positive high correlation. That means the ranks from the two judges are high. They are almost the same. If you look at it, they have a positive, because first of all 0.8 is positive, and it is very high, it's close to 1. So there is positive, there is a highly positive, there is a very high positive, just like the like 0.9 upward, 0.95, and so you can say those ones are very high positive correlation. But this one 0.8 is highly positive, or positive high correlation. If it is 0.5, you can say it's moderately correlated. Plus 0.5 is positively moderate. So the correlation is positively moderate. If it is minus 0.5, the correlation is negatively moderate. It's negatively moderate. So when there is a negative sign, the correlation is negative. When there is positive sign, remember your arrow takes value, it takes value minus 1 less than or equal to arrow less than or equal to plus 1. So it takes value between minus 1 and plus 1. So when it's plus 1, it's perfect positive correlation. When it's minus 1, it's perfect negative correlation. When it's plus 0.5, it's positive moderate correlation. Minus 0.5 is negative moderate correlation. Then when it is low, 0.2 plus 0.2 is very low positive correlation. Minus 0.2 is very low negative correlation. Then when it is 0, you calculate your R. It's possible for you to calculate your R, your correlation coefficient, and you get 0. It means there is no evidence of correlation. Now I will bring us later to what we call the coefficient of determination. The coefficient of determination is used to explain is used for the explained and the unexplained variation in Y. The explained is used to calculate the percentage of the explained and unexplained variation in Y. So you can see that 0.8 indicates a positive high correlation. So the two judges are not too far in their decision. They are highly correlated, though not perfect, but it's the relationship between their decisions is very high. The relationship in the decision from the two judges in the beauty competition is very high. Now this is how we use the Spearman Rank Correlation for the ordinal data, the ranked data, the qualitative data, and you can see there are no ties in the ranking. Now we can also use the Spearman Rank Correlation Coefficient for continuous data. Now let us take an example. Permit me to clean this part of the board. We are going to take an example and see how we can use the Spearman Rank Correlation Coefficient to calculate the linear correlation for continuous data. Now permit me to take a third example for this video. I call it example 3. The data before us are scores from a particular exam. The score were ranked upon 150. So let's take a look at it. We have our X and our Y. Yeah. From the scores below, calculate the rank correlation coefficient. You see, the rank is already there. So that means it's the Spearman rank correlation we are going to use. So our X, let's go ahead now. X has 80, 75, 95, 95, 65, 70, and 50. They are 1, 2, 3, 4, 5, 6. They are 6 in number. Then Y has 100, 95, 102, 130, 100, and 110. Now take a look at this. Y has a tie. Y has 100 and 100. So I'm going to show you how to break a tie. Now let me just quickly give this example. If I have X here, let me use this to explain how we can break a tie. If I have X to be 5, 6, 7, 5, 6, 7, 5, 5, 5, 6, 7, 5, 5, 6, and 4. And I want to rank X. Please watch carefully how I'm going to rank X. Look at this data now. It has series of ties. They are quantitative data, not qualitative. When you are doing linear correlation for qualitative data, you don't expect to have tie. Because when you are ranking beauty, intelligence, no two people or no two persons can be equally beautiful, no two persons can be equally intelligent. There must be certain criteria to differentiate their intelligence or their beauty to make one be on top of the other. So you have to understand that. Now look at this. These are continuous data, quantitative data. You can see 5 appearing 3 times. You can see 6 appearing twice, then 7 and then 4. Now how do you rank? You can rank by starting with the highest value or the smallest value. I come again. You can rank by starting with the highest value or the smallest value. Is not wrong. You assign 1 to the highest value, then 2 to the next, 3 to the next of that one, 4, and so on. Or you assign 1 to the smallest value. So I come again. You can rank by starting with the highest value or the smallest value. So I want to show us how to rank this set of data now. Look at it. The first thing I'm going to do, I want to start with the highest value. The highest value here is 7. So I'm going to give 7 position number 1. Then what is the next value here? The next value in X is 6 and 6. So you can, these two now, they are equal in scores. How do you do? That means this one take the second position, this one take the third position. So you are going to take their average. So this will be 5 over 2, and that is 2.5. So you are going to assign 2.5 to this 6 and 2.5 to this 6. That is how you break the tie. You take the average of their ranks and you allocate it to them. You take the average of their ranks. So the first one here is 7. Then 6 are equal, you break, because these data are continuous data, they are quantitative data, so you can break tie by taking the average of the ranks. Then the next one, remember, you have occupied the second and the third position. Then look at the next one now is 5, and we have 5 in 3 places. That means we have occupied first, second, and third position. The next position we start from the 4th position. So this 5 you can allocate it the 4th position, this 5 plus the 5th position, this 5 plus the 6th position. Because they are 3 in number, you take their average. This will now be equal to 15 over 3 is equal to 5. So what do you do now? Their average is 5. The average of the 3 ranks is 5. So you are going to allocate 5 to each of them. Then what is the next rank? The next rank, of course, now you have occupied the first, second, third, fourth, fifth, and sixth. The next one will be the 7th rank, which is 4. You can see that now. So count the number of data: 1, 2, 3, 4, 5, 6, 7. So this is how you rank when you have tie. That is how you break tie. That is how you break tie when ranking. So since I've used this to explain, breaking this tie here will not be a problem. It will not be a problem to break the tie. So permit me to go back to my ranking of this continuous data. So if I come here now, I will have, permit me to clean this part. So now, calculate the rank correlation. So that you have it here. So permit me to rank my X here. I want to rank my X. Now, remember I said you can rank from the highest value. You can also rank from the smallest value. I want to rank from my first value, my highest value. The highest value we have for X, observation here, is 95. So 95 will take the first position. The second one is 80. 80 will take the second position. Then the third one is 75. 75 will take the third position. Then the next one is 70. 70 will take the fourth position. Then the next one is 65. It will take the fifth position. Then the last one is 50. 50 will now take the sixth position. Then let us rank our Y. What is the highest value of Y there? Is 130. So 130 will take our first position, followed by the second position is 110. Then the third position is 102. Then of course the fourth position and the fifth position, they are tied, 100, 100. Fourth, fifth. So you now come here, you now say 4 plus 5, because they are 2. A number you divide by 2, this will be 9 over 2 is equal to 4.5. So you come, you allocate 4.5 here, and you allocate 4.5 here. While the smallest value there, which is 95, will now be the fourth and the fifth positions have been allocated. Then of course the average taken, then this will now be the sixth position. That is how we have done the ranking. You can see it is as easy as that. It is as simple as that. So now we want to calculate our D. Our D is equal to rank of X minus rank of Y. Then of course we come there. The formula says D square. We will now come out and have our D square. 2 minus 4.5, this will be minus 2.5. 3 minus 6 will be minus 3. 1 minus 3 is 2. 5 minus 1 is 4. Then 4 minus 4.5 is minus 0.5. 6 minus 2 is 4. So now we are going to square each of them. Minus 2.5 square will give you 6.25. Minus 3 square will give you 9. Minus 3 square will give you 9. Then 2 square will give you 4. 4 square will give you 16. Minus 0.5 square will give you 0.25. Then 4 square will give you 16. Then when you take the total, you are going to have 51.5. That is what you are going to have. You are going to have the sum of the D square to be 51.5. It is as simple as that, 51.5. So calculating the rank correlation using the Spearman rank correlation, we have P into RHO is equal to 1 minus 6 into 51.5 all over this division line doesn't cut across to where the 1 is. Our n is 1, 2, 3, 4, 5, 6. It will be 6 into 6 squared minus 1, because it's n into n squared minus 1. So this value will be arrow HO will be equal to 1 minus 6 multiplied by 51.5. It will give us 309. 309 all over 6 squared is 36. 36 minus 1 is 35. 35 into 6 will give you 210. So you are going to have this will be equal to 1 minus 301 over 210 will be 1.47 minus 1.47. So our value for the rank correlation will be equal to minus 0.47. So you can see this one is slightly negatively moderate. 0.5 is moderate. It's around 0.5. So it's negative. Minus 0.47 is almost moderately negative. So it indicates almost negative, or moderate, or almost moderate negative correlation. Almost moderate negative correlation. So it's almost average, but it is negative. So the relationship between X and Y, the direction is that it has a negative relationship. So you can see how we have been able to break tie when the data are continuous or quantitative. So we can also use the Spearman Rank Correlation Coefficient to obtain linear correlation for continuous data, for quantitative data. I hope you have learned something beautiful today. This is how far we can go. But before I go, let me tell us about what we call the coefficient of determination. There is what we call the coefficient of determination. It is used to analyze the explained and the unexplained variation in Y. So permit me to have it here. So the coefficient of determination is called R square. Now, if R is equal to, maybe we calculated the other than 0.8, now the coefficient of determination R square will be equal to 0.8 square is equal to 0.64. Of course, the coefficient of determination will multiply by 100 in percentage. So this simply means that 64% of the variation in Y is explained. So if 64% is explained, then of course you take 64 away from 100, it means 36% is unexplained. So anytime it is wrong, one mistake people use or make when interpreting the correlation coefficient is that they multiply the correlation coefficient directly by 100. Somebody, for instance, will now multiply 0.8 by 100, getting 80%. I'm now using 80% as the explained variation. It's wrong. It is the coefficient of determination, R square, that we use as the explained as the explained variation. So when you square the correlation coefficient, you get the coefficient of determination. When you multiply it by 100, you get the explained variation in Y that is explained. Are you getting me? The variation in Y that is explained, then the unexplained, then you subtract it from 100 and you get the remaining one. So 36 is unexplained. So beloved, I hope you have learned much about correlation. You have learned a lot about linear correlation today. You have seen the difference between Spearman Rank Correlation Coefficient and the Pearson Product Moment Correlation Coefficient. We can use the Spearman Rank Correlation Coefficient for qualitative and quantitative data. For qualitative data, the ranks, there are no ties in ranks. But for the quantitative data, there may be tie in ranks. Like for instance, I told you qualitative data are data that cannot be measured numerically, like beauty, like character, like behavior, and the rest of them. So like I gave an example in a beauty pageant where you have 5 girls, then you have 2 judges, X and Y, they want to judge these girls based on their beauty. So no 2 girls are equally beautiful. So when you are doing the ranks for qualitative data, there are no ties. You just rank it from the first to the last. But when you come, you talk about quantitative data. Quantitative data are data that can be measured in numbers. Example, weight, height, student scores, and so on and so forth. 2 students can be of the same age. 2 people can be of the same weight. 2 people can have the same score in exam. So they can be ties when you are dealing with continuous data or quantitative data. So you break tie by taking the mean of the ranks and you continue from the next rank. That is how ties are broken. So now I believe you have learned much about the linear correlation coefficient, how to interpret your results, and how to get your coefficient of determination to get the explained variation and the unexplained variation. That's one of the mistakes people make in interpreting the correlation coefficient. Please, I am glad you were able to stay to the end of the class. Wait for my next video on multiple regression analysis. I will be dealing on multiple regression analysis in my next video. Thanks again for watching. My name again is Dr. Chris Esekaibe. Please subscribe to my YouTube channel. As you do, God will bless you. God will bless you. Subscribe to the channel. Share my videos on your YouTube channel. Share them in your WhatsApp platforms, in your Facebook. Share them around and be part of those sharing knowledge across the globe. And as you do, God will bless you. Enjoy the rest of the day. Bye.